This video is on 12.2, two-way tables and probability. Um, so let's go ahead and just start with some definitions. So there's a lot of definitions on this page. We're going to talk about each one individually. You may want to write these down. So two events are considered to be mutually exclusive if they cannot both occur at the same time. So, for example, if we were drawing one of our Venn diagrams, here's event A occurring, here's event B. So mutually exclusive events would have no overlap. There would be nothing they have in common. There's two things that cannot happen at the same time. So for example, if I have a piece of candy or if I have a bag of candy and I'm drawing out a piece, the piece that I draw out can't be two different types of candy at the same time. Okay, so event A would be drawing out an M&M. Event B would be drawing out a Skittle. I can't get one piece of candy out of a bag and have it be both. So those would be mutually exclusive events. Two or more events are said to be overlapping events if one or more events occur at the same time. So on this one, we're going to have some overlap. So let's say event C is drawing out an M&M and event D is drawing out a red piece of candy. This overlap right here would be candies that are both red and an M&M. So that's called overlapping events. Okay. The multiplication rule is a rule that says if we have more than one event occurring, the probability that they both occur is their individual probabilities multiplied together. And that's only true as long as the events are independent. Okay. So what does it mean for events to be independent? Independent events are events in which one occurring has no influence on the other event occurring. So for example, if I toss a coin and I get heads and I roll a die and I get a 5, those two events have no influence on one another. Like tossing a head or a tail has no influence on which number I'm going to land on when I roll the die. So those are independent events. So if I wanted to use the multiplication rule here, I could say that the event, if I'm doing both, if I'm tossing a coin and I'm rolling a die, the probability of both getting a heads on the coin and rolling a six-sided die would be the two individual probabilities multiplied together. So the probability of getting a head, if I'm tossing a die, is 1 out of 2. The probability of rolling a 5 on a six-sided dice is 1 out of 6. So to get the probability of both of them happening, I would multiply these together. So I would have 1 over 12. And I could go ahead and change that to a percentage by using my calculator to divide 1 by 12, which is equal to 0.083 repeating. And then I would times that by 100 and round it off to a tenth or so, and I would get 8.3%. Okay. So we can only use the multiplication rule when the events are independent. Okay. So now we're going to look at some two-way tables. If I can get the slide to change over. So what a two-way table is it's just a way to organize data if we have more than one thing going on at a time. So this table is comparing the number of boys to the number of girls in a study, as well as whether they prefer to have their potato baked or mashed. So there are two different attributes, gender and how they like their potato. We're comparing it all in one chart altogether. So a couple things about this chart. All of the rows and columns should add to the total on the ends. So of all the people that we surveyed, there were 58 that were both boys and like baked potatoes. There were 63 that were girls and like baked potatoes. And the total of those people who preferred baked potatoes was 121. So 58 plus 63 does equal 121. Also, the total number of boys that were surveyed was 100. 58 of them preferred baked potatoes and 42 preferred mashed. So if we add those two together, we should get the total number of boys, right? Same thing for the girls. And then the grand total number of people in the study is right here. There were 200 altogether, and it looks like half and half boys and girls. Okay, so we can use these tables in probability, and this kind of helps just organize the data and kind of helps us see more easily what the probabilities are of certain things. So let's look at another two-way table. So here's a table that we have on this side. We have has tuberculosis or does not have tuberculosis. Excuse me. And on the other side, we have whether the test is positive or the test is negative. So if they're tested for tuberculosis, sometimes we get false negatives or false positives. And so this is people who actually we know has tuberculosis. These people do not have it, but their testing sometimes is a little bit off. So we need to fill in the missing parts of this table. So in order to do that, we need to think about how this would add up. So I know that the people who have it and the people who don't have it should add up to the total number of people. Let's see, the people who test positive and have it, and the people who test positive and do not have it should add up to the total number of people that test positive. And so in order to find this, I know that the people who test positive that have it and the people who test positive that do not have it should add up to 423. So in order to find how many do not have it but test positive, I can just take my total, which is 423, and subtract how many have it and tested positive, which is 361. So 423 minus 361 is 62. Now that we know that number, we can use that number to find out our total number of people that do not have tuberculosis. So we're going to add 62 to 558, and that gives me 620. And now we can use the total that have it and the total that don't have it to get the total number of people. So 620 plus 380 is 1,000. And now we can fill in these other blanks. So I know 423 plus the people, all the people who test negative should equal 1,000. So 1,000 minus 423 is 577. The people who have it and test negative should be the difference of these two, the total minus 558, which gives me 19. And then just double check and make sure it adds up every direction. Okay, so 361 plus 19 is 380. It looks like we're good. So everything is adding up correctly. So basically some of the task today will just be making sure that these tables are filled out correctly, that you understand how they work, that you understand that the columns should add up to the total, the rows should add up to the total. Okay. So in order to complete this table, we just again need to think about that all of the rows should total to this total, the column should total to this one. So I know that 25, the number of boys who prefer to swim for exercise added to the number of girls that prefer to swim should equal 64. So in order to find that, I'm just going to take 64 minus 25, and I'll get 39 girls here. I know that there are 25 boys who prefer swimming. There's a total of 45 boys, and so I need to subtract 25 from 45 to get the number that prefer the gym. Down here I can find the total. There's 100 people total. There are 64 that prefer swimming, which means 36 prefer the gym. 36 minus 20 would give me 16 here, and then 39 plus 16 is 55. So we're just making sure that all of the columns and all of the rows add up to the total numbers here. Okay, so now how can we use these tables for some probability? And we're actually just going to use the same tables. We're going to go back here. Okay, so if I were asked the question, I'm given this data. Think of like all of these people's names being put, like we put their name and what kind of potato they prefer, and we put it in a bag, and we randomly draw one out. what would be the probability that one of the people that we drew out of this group, what would be just the probability that they're a boy? So the probability that they would be a boy in this group would just be the total number of boys over the total number of people, right? So there are 100 boys total, and there are 200 people total, which means the probability of getting a boy, if we drew out a name, if all of these people's names were in a hat or a bag and we drew one out, there'd be a 50% chance that we got a boy. What would be the probability that we draw out a person who prefers mashed potatoes? Okay, so the probability that the person prefers mashed potatoes, it would be the total number of people over the total number, the total number that prefer mashed over the total number that are in the study. So this would be 79 divided by 200, which is equal to 0.395, which would be 39.5%. Okay. All right, so let's find something that's a little bit more interesting than that. What is the probability that the person that I draw out is both a boy and prefer mashed potatoes? Now, in our probability notation, we learned that and is the same as intersection, right? That upside down U kind of looks like a capital A without the cross on it. So I could use and or intersection. These both mean the same thing, okay? Basically, we just want to know if we were to draw a person out, what is the probability that they had both of these qualities? They were both a boy and they prefer mashed potatoes. And remember, this upside down U is called an intersection. And literally, we are just going to look in the table for the intersection of boy and mashed. So I look at boy, I go across. I look at mashed, I go down. That intersection right there where they intersect, that is the number that we want on the top of our probability. And then it's always going to be out of the total number of people. So 42 out of 20 or of 200 would be 0.21, which is 21%. Okay, so let's try another one. What's the probability that the person that we choose out would be a girl and or intersect, they prefer baked potato? Okay, again, if it says and or has that intersection sign, I can use either one. They both mean the same thing. I'm going to find the actual intersection of girl and baked potato. So girl goes across this way, baked goes across this way, girl and baked intersected at 63. So 63 out of 200, which would be 0.315 or 31.5%. All right, let's just try one more thing. What's the probability that they prefer baked and or intersection, right? They also prefer mashed. Okay, this is a case of mutually exclusive events. They were asked to choose which one they preferred. So they may really not have a preference, but they had to choose one. So someone can't prefer baked and mashed at the same time. Okay, so that would just be 0% chance because baked and mashed are mutually exclusive events. They can't happen at the same time. Okay, this is getting pretty messy. So let's move to a new chart. So what if I were asked on this chart, looking at this data, what is the probability that a person tests positive for tuberculosis? So again, this 1,000 people are the people that were the data was collected on. So it's like taking these 1,000 people, putting their name on a piece of paper, writing down whether they had tuberculosis, whether they tested positive or negative, mixing them all together in a hat and pulling one out. What's the probability that the person I pulled out would test positive for tuberculosis. So I would need to take the total number that tested positive, which would be 423, and I would need to divide it by the total number of people in the study, which would be 1,000. So this would equal 0.423, which would be 42.3%. Okay. I could also do something like, what is the probability that they test positive and, or intersection? I could use either symbol, the intersection symbol or and, they both mean the same thing. So what's the probability they test positive and they also have tuberculosis? Okay, so that, again, when it's and or that intersection, I'm literally looking for the intersection of test positive and has tuberculosis. So that would be right here. All these people, 361, both test positive and actually have it. So it would be 361 out of 1,000, which would be 0.361, so 36.1%. Okay. So the one that we haven't talked about yet is our union or our or, right? Remember, union and or are the same, just like intersection and are the same. So if I see the probability of test positive and has tuberculosis, and I do the union here, so it'll either say union or, that is meaning that if I were to draw a person out, they would either test positive or they would have tuberculosis. So it's a little bit different than the intersection or the and. It doesn't mean this person has both. It means this person has one or the other. They either test positive or they have tuberculosis. So on this one, we have to treat it a little bit differently. We have to take the probability of all the people who test positive. So the test is positive. There's 423 total people that test positive out of 1,000. And then we would need to add on the probability of the people who actually have tuberculosis. Okay, we're adding all these up because we're doing a union. Remember, throw them all in the bowl. 380 people have tuberculosis out of the 1,000. But now think about this. If we have just added up all the people who test positive, which is 423, that adds 361 to 62, right? And we have also added in all the people who have tuberculosis, so that's 361 plus 19 to get the 380. That means this 361 people, they got added to both of those totals, right? They got added in as a person who tests positive, but then they also got added in again as people who have tuberculosis. So they're in both of that. 361 is in both of these numbers, which means we added these 361 people on twice to our probability, which means we need to subtract one of them back off. So we would have 423 out of 1,000 plus 380 out of 1,000 minus those 361 people that got counted twice. They got counted both as a person who tested positive and as a person who has tuberculosis. So we need to subtract them off once. So if I add this all up, remember when you're adding and subtracting fractions, that common denominator is just going to stay the same. It's just the numbers across the top that we're going to be adding and subtracting. So it would be 423 plus 380 minus 361, which is equal to 442. So 442 out of 1,000, which would give us 0.442 or 44.2%. Okay, so that would be the probability that they either test positive or have tuberculosis. Okay, let's skip ahead to the next chart. So I have a lot of room here. Okay, so this one is comparing whether they are a boy or a girl, also to whether they prefer swimming or the gym. So let's do some probabilities here. So what is the probability that a person that I draw out at random of these 100 people are a boy or they prefer the gym. Okay, so this person, I draw this person's name out of a hat. What is the probability this person is either a boy or they prefer the gym? So if I want to find the probability that this person is either a boy or they prefer the gym, I need to add those probabilities together. So the probability that they're a boy would be 45 out of 100. The probability that they prefer the gym would be 36 out of 100. There are 36 out of 100 people who prefer the gym. But now, the boys that prefer the gym, these 20 people, they were added on both as a person who prefers the gym and as a person who is a boy. So they were added on twice, which means we need to subtract them once. So this would basically be 61 out of 100, I think, if I did my addition correctly. Let's just double check it really quickly. 45 plus 36 minus 20. Yeah, it was 61 out of 100, which is 61%, right? So there are 61% of the people who are either a boy or they prefer the gym. The probability that they are a girl and or intersection, they prefer to swim. Okay, remember, if it's and or that intersection, that one means they have to be both. The person that I draw out, what's the probability that they are both a girl and they prefer swimming? So that would just be the intersection of swim and girl, which would be 39 out of 100, which is 39%. Okay. What is the probability that they are a girl and or union, I'm sorry, or union that they prefer to swim or sim? So they are a girl or they prefer to swim. So when I pull out that name, it could be either one, a girl or they swim. What's the probability that this person is either a girl or they prefer to swim? So girls, there are 55 out of 100, plus the people who prefer to swim, which is 64 out of 100, minus the people that are both, because they got counted both as a girl and as a person who prefers swimming. So they got counted 2 times. So subtract off 39 here. So 55 plus 64 minus 39 is 80. So 80 out of 100, or 80%. All right, so last thing we want to talk about today is on your assignment, you're going to be asked to be thinking about some probabilities with cards. So this is the sample space for choosing a card from a deck of standard playing cards. So if you haven't played with these a lot, you may need to use this chart and to think about this. So the way that it's set up is there are 4 suits: hearts, diamonds, clubs, clubs and clovers. Aces, they each go from ace, which is kind of like 1, up to jack, king, and queen. So they go ace to 10, and then jack, queen, and king. Jack, king, and queen are called face cards. Okay, so those are the face cards. And then the others are number cards, and then we have aces. So if you're asked to find probabilities for this, this is the type of thing, or this is what kind of the visual that you can look at to find those probabilities. Notice that the hearts and the diamonds are both red, and the aces, sorry, I keep saying ace because I see the word, and the clubs and clovers are both black. Okay, so you may be asked something like, what is the probability that I get a red card if I were to draw one out of this deck? So there are 13 cards in each suit. Each of these is called a suit. And altogether, there are 52 cards in the deck. So half of them are red. So each of these has 13 cards in it, right? So 26 out of 52 of them are red, or 50%. So the probability that if I just draw one card randomly from the deck, that I get a red would just be 50%, 1 out of 2. What is the probability that I get a jack and a red? Okay, so remember that's intersection. So that's saying that if I pull the card out, it has to be both Jack and red. So there are only 2 cards in the deck that are both Jack and red. So the probability would be 2 out of 52. And I'm not gonna change that to a percentage, but I do want you to do that. What would be the probability that they are a Jack or, remember that union means or. What's the probability they're a Jack or they're red? Okay, so this is a different question, right? Now I need to think about how many cards are Jacks added to how many cards are red, and then subtract off how many are both. So just kind of like in the table. So there are 4 Jacks altogether out of 52. How many red cards are there? Half of them are red, so 26 out of 52 are red. But these two Jacks are red, so they got counted both as a Jack and as a red card. So we need to subtract off 2 out of 52 to get the total number. So this would equal 28 out of 52. And you could change that to a percentage. Okay, so that's basically it for what you'll need today for your assignment. If you have any questions, please feel free to email me and we will work those out. Have a great day, guys.